What is up, everyone? Welcome back to the Marble Project. My name's Kiro, and today we're gonna talk about forces.
May the Force be with you.
Alright? So this is something we've always heard of. It's a force.
May the Force be with you.
Okay? And what is a force?
May the Force be with you.
Well, to understand it initially, we'll just say a force
May the Force be with you.
is a push or a pull. Alright, so if I push you away from me, I applied a force on you. If I pull you back towards me, I applied a force on you. Alright? And what do you know about opposite directions between a push and a pull? They're just different directions. They're inverses, alright? One's negative. So, what is a force in physics? Well, I hope most of you would be familiar with Newton's second law, and that states that F equals ma. Okay, and we can look at the components here. Alright, so force. This is what we're trying to analyze, force here. What about mass? Okay, what's mass? Well, it's a scalar. It doesn't have any direction. Alright, it's just mass. What about acceleration? Acceleration has a direction. So what is it? It's a vector. So we know force is a vector, and it's a scaled version of acceleration. So it's going in the same direction, but it's scaled based off of the mass. Alright? So if we have an acceleration vector on an object, so we say that we have a box, and it's accelerating this direction. Okay, with mass m and acceleration a. Well, that means a force is being applied to that box in the same direction as acceleration of magnitude ma. Okay, and so what about like force vectors? Well, it's just like any other vector, so you can split it up into its vector components. Say I have a box right here, and it's on a plane. Alright, and there's a force going this way with an angle of theta to the level. This force vector can be split up into the x and y components. Okay, x and y. Alright, and so there are a few different kinds of forces, or just fundamental forces, and we'll keep this box. So what do we know? We know there's gravity. We know that acceleration due to gravity, if the box is sitting on this ground, is always straight down. We know acceleration is 9.81, and we know the box has a mass. So we know the force going down on gravity, due to gravity, is equal to m and g, which is 9.81, and m is the mass of the box. But what do we also know? If you put something down on a table, it doesn't move. And we know that force is equal to mass times acceleration. So it's not accelerating. That means there's another force acting on it in the y direction. And this is what we call the normal force. Okay? So now we have two forces we know. Alright, so forces. We know that we have gravity. We know that we have the normal force. And normal, why? Because it's always perpendicular to a surface. So right here, what do we know? So here we have a normal force going straight up. Okay? But what if, say we had something else. Say we had an incline. We put a box on it. We know gravity goes straight down, and the normal force, it's normal, it's perpendicular to the surface. So the normal force is right here. So this is gravity, and this is normal. Okay, and what do we know when we put a box on an incline like this? It's not moving up or off the incline. So we know that there's another force here, alright? We know that there's a normal force. We know that there's a force here. And what's that force? It's the vector component of gravity in this perpendicular direction. Alright? So we know because we know gravity pulls down here. We know gravity pulls down in this red direction because it's straight down and that's the component of it. And because we know that, we know then that there has to be another force of equal magnitude going up on it. And that's the normal force. Okay, so now we can think about the magnitude of the normal force. Well, we know that it's exactly opposite of this component of gravity. So what's this component of gravity? Well, it's mg because that's the magnitude of gravity. And we take the vector component, so if this angle is theta, then we know that the normal force is equal to mg cosine theta, where theta is equal to the angle between the perpendicular here and gravity. Alright, so theta is equal to this angle right here between straight down, which is gravity, and perpendicular to the surface. Okay, so let's try an example of a ramp on an incline. So let's draw our big incline here. Whoop. Okay, with an angle theta, and we'll put a box on it. And we'll draw our axes with respect to the box. We'll draw those in red. Okay, and we can analyze forces on the box in blue. What do we know? We know if we go straight down, that's gravity. Force due to gravity. And we know this angle theta here is equal to this one. Okay, and there's a geometric proof with triangle similarity to go through that with this triangle and that triangle, but I won't get into that. So we know gravity's here. We know it has vector component, one going this way and one going this way. And what do we know? We know because there's no acceleration right here in this area, we know then that there is also a normal force acting up right there. So where does the box slide now in all of this? Well, this portion of gravity and this portion of the normal force cancel out. So where's the net force? The net force is just this one. It's this portion of gravity. So where's the box going to accelerate? It's going to accelerate down the incline. So that's the direction. And the magnitude is going to be this component of gravity. And how can we see that? Well, we know that is Fg sine of theta. Okay, and if we want to know the magnitude of the normal force, it's Fg cosine of theta, because that's the component of this vector, and those two vectors are equal in opposite directions. Now we also have friction. Everyone knows friction, you know? Slide your hands together. They get hot. Friction. Try to move something. Stuck on the ground. Friction. It's hard to push. Okay, and what's friction? Well, we can think about it. If we have a plane right here, draw it in black. If we have a plane right here, a straight plane, straight enough, and we have a box sitting on it, and we try to apply a force here, going that way. Okay? So we apply a force going to the right. Something, it's gonna move, it's gonna accelerate because of Newton's second law, F equals ma, but that's the net force. The net force, so the sum of all the forces acting is ma. So what do we know now? We can draw our vectors, or our forces in the y. We have gravity going straight down, and there's no acceleration in the y. It's not sinking through the ground, so there has to be an equal force going up. That's the normal force. Okay, and how does friction work then? Well, friction, we know if we're pushing it to the right, we know friction has to be going to the left And we know that friction going to the left has to be less than the applied force to the right, because we know that we can move it. Okay, so how's this gonna work? We know that this force, the magnitude of this force is greater than the magnitude of that force. And we know that this is an applied force, so this has to be given. And we know here gravity and the normal force. So how do we find the frictional force? Well, we know frictional force, so the force from friction is proportional to the normal force. And what does that mean? Well, what's the normal force? The normal force is this force going up. Okay, and if we did have an incline with a box on it, then the normal force would be going up here. So why is it proportional to the normal force? Well, the normal force, okay, if we were to come down here and draw our incline again, really big, and we know gravity goes straight down, and the normal force is perpendicular up here. What determines the normal force? Well, it's equal to gravity going straight down. But what's gravity going straight down? What's that force? It's how hard two things are pushed together. Okay, so the normal force is how hard things are pushed together. And that's why friction is proportional to it. You think of it, if you push harder down on something, it's going to be harder to slide it. Okay, if you squeeze your hands really tight, try to move it, it's hard. But if you just gently touch them, it becomes a lot easier. So now we know friction is proportional to the normal force, and it's linearly proportional with a proportionality constant, which we call mu. Okay? And what's mu? Well, it's a Greek letter. Alright? And this is the coefficient of friction. So coefficient of friction. Okay, and if we know that, we know it's linearly proportional, so what can we say? The magnitude and the direction of the frictional force is equal to mu times normal force. What do we know? We know these are vectors. Okay? And we know that this right here, what is it? It's a scalar. Alright? It's a coefficient. It doesn't have a direction. But what do we also know? We know the units of force have to be equal. Because this is a force and that's a force, so the units have to be equal. So what does that mean? If we can solve for mu, we can divide both sides by the normal force. And we can look at units. If we look at units, we see this is newtons divided by newtons, or units of force divided by units of force. So we know that mu has no units, or it's dimensionless. Okay, so mu is dimensionless. What does that actually mean? Well, it means that it has no units. It's just a proportionality. Okay? So the coefficient of friction, mu, is just a way, it's a proportionality to relate the frictional force and the normal force. So now, we'll get into two different types of friction. Static and kinetic. So let's think about what these words mean. Static, stationary, not unchanging. Kinetic, the first part, we've seen this before, kind, from kinematics, it means moving. And what does this mean? Well, it just means that there are two different coefficients of friction when stuff is stuck together, stationary, and stuff is moving. Alright, and that's because if two things are stationary, stuck together, there's some like atomic bond, or keeping these two together. But if two things are already moving, okay, they're already moving, then those bonds are they're weaker. All right, and that's due to chemical properties or atomic properties, sliding two things together. But what does this mean? It just means that friction has a lesser effect when stuff is moving. Okay, so what does that mean? It means if you start with a box on the ground, it's really hard to get it to start moving. But as soon as it is moving, then it'll just keep going. We'll draw our box again. And we want to start applying forces in increments. So we're going to apply a force here. It's going to be small increments. We know what there will be a force of friction resisting our push. Okay? So what's going to happen? I apply a force. We'll call this force F applied. Okay? And as the applied force goes up, so does the frictional force. Okay? But what do you know about the frictional force? If I don't apply an applied force, there won't be a frictional force. So we know that the maximum friction, max, is equal to the normal force times the static coefficient of friction. But it's not always equal to that. If I don't apply a force, there won't be a frictional force. So it increases as the applied force increases until it gets to this maximum threshold. And once it gets there, it's overcome, and suddenly this doesn't apply anymore. Because now suddenly the force resisting it has become the normal force times the coefficient of kinetic friction. Why? Because it's already moving. It's not stationary anymore. So once you overcome the initial threshold of the static friction, you get into kinetic friction, which has a lesser magnitude.